Today we want to talk about magnetic fields. And honestly, they're magical and mysterious and seem to make no sense how you can put two magnets in proximity to each other and get a pretty large force of attraction or repulsion, depending on the orientation of the magnets. Before we talk about magnetic fields, we need to talk about gravitational fields. And a gravitational field occurs when there is mass. Because the Earth has mass, it warps the space around it, and that warpage of space puts a force on other masses. So the presence of mass creates a gravitational field that puts force on other masses. If an object has charge, like an electron here has negative charge, and a proton has positive charge, because those objects have charge, they warp the space around it. The space now will put force on other charges. So positive charges are attracted to negative charges through this mutual warpage of space. All right, so if gravitational fields are produced by mass and electric fields are produced by charge, what do you think produces magnetic fields? And you might not guess, but it's when charges move through space. When charges move through space, they warp the space in yet a different way. So when charges move through space, they warp the space, and the space will now put a force on other moving charges. So if I had a positive charge down there and it's stationary, there's no magnetic field. But if that charge moves, it only has a magnetic field while it's moving. And when it's stopped, there's no magnetic field. So magnetic field when it moves, and as it slows down, no magnetic field. Hans Christian Ørsted was getting ready for a lecture back in 1820, and he had a battery and some wire on his desk, and he also had a compass. And he noticed when he turned the battery, or when he connected the battery, the compass was sitting underneath the wire. And when current was running through the wire, it deflected the compass. First time anybody had ever seen that, and it was mind-boggling. So here we have a battery supply, a power supply. We have a circuit connected from positive to negative, and we have a compass sitting underneath the wire. And right now, there's no magnetic field other than Earth's. Earth's magnetic field is pointing down and right over here. It's pointing off in that direction there. And when we flip the power on, look at the needle, it deflects to the right. But if I put the compass on top of it, the compass now deflects to the left. So if I had a wire here and I connected it to a battery, when the compass is under the wire, the magnetic field is in one direction. If I put the compass on top of the wire, the magnetic field is in the opposite direction. And that was just looking below and above. If we place the compass in front of the wire, we would find the magnetic field goes up, and behind the wire, the magnetic field is down. If you do it at a variety of different spots, we would find that the magnetic field goes around the wire. So when current goes through that wire, there is a circular magnetic field going around the wire. So if a proton were moving this direction, there'd be a magnetic field around the proton like that, warping the space. I'm sorry, if it was an electron. If it was a proton, the magnetic field would be the exact same, but the exact opposite direction. Now, if a charge is stationary, there is no magnetic field. If that charge moves, there's a magnetic field. But we have to remember that all motion is relative. So if that charge is moving relative to an observer, there is a magnetic field relative to the observer. If the observer is running alongside, then that charge is not moving relative to the observer. So the person there would not see a magnetic field because it was not moving relative to that person. So if I had a compass under a wire and I had these positive charges moving through the wire, it will deflect the needle to the left, because we can see that under the wire, the magnetic field is to the left. Above the wire, the magnetic field is to the right. If they were negative charges going through the wire, the magnetic field would be in the exact opposite direction, and the compass would deflect to the right. But now here's where the wild thing comes. If I had a compass moving at the exact same speed as the charges, there would be no deflection of the needle because there'd be no magnetic field. Or I thought that would be the case, and it turns out it's not the case. What I forgot was that even though electrons are moving through the wire like that, there would be protons stationary in the wire, and the compass is moving relative to the positive charges. And the compass needle deflects to the right. And that the reason is because the positive charges are stationary, but they're moving relative to the compass, just as if the compass were stationary and the positive charges were moving down and the electrons were stationary. So because we have an equal number of positive and negative charges, it's the current that's going to running through that wire that's going to create the magnetic field. When we studied angular momentum, we learned a right-hand rule. It helped us to understand angular momentum when things are moving in circles. Well, a magnetic field is something moving in a circle. So if this positive charge was moving to the right, we know that there would be a magnetic field going around that positive charge. Well, what direction around that charge does it go? What we do is we take our right hand and we point our thumb in the direction of the movement of the positive charge, which is conventional current. And then our forefingers are curled around in the direction of the magnetic field. So if that positive charge moved to the right, there'd be a magnetic field around the charge in the same way our fingers curl around our hand. It would be going toward us on the top of the charge, and the magnetic field would be going away from us under the charge. In front of the charge, the magnetic field is going down. Behind the charge, the magnetic field is going up. Again, the magnetic field goes around the charge. So if I took a wire and hooked it up to this battery here, we know that conventional current goes from positive to negative. So the current is going up like this. So we would point our thumb, if I had my thumb a little more straight, we'd going straight up. And the magnetic field would curl around like this, to the left, under the wire, and to the right, above the wire. The magnetic field would be going around the wire, just like our fingers go around like this. So if we had a compass there, under the wire, it would be deflected to the left. Above the wire, it would be deflected to the right. Right? So that's the right-hand rule with moving charges. If I took that wire and folded it onto itself, so it's going to the left on the bottom and to the right on top, there's going to be magnetic fields of all those charges. And what's going to happen is the magnetic field, we have two different magnetic fields or two different directions. And because they are equal and opposite, there will be no net magnetic field. It's a great way of canceling the magnetic field around a wire, is just have the same amount of current going in the opposite direction. You'll have the same amount of magnetic field in the opposite direction. It will just cancel. Now, if we take a wire and we fashion it into a loop, we'll call it a coil, and current goes from positive to negative, and if we applied our right hand at all these spots underneath, we can see that overall, on the inside of that coil, the magnetic field is going to be going into the screen. And on the outside, all the way around here, the magnetic field is going out of the screen. Now we have a convention to help us draw that, and it's related to an arrow. That an arrow, there is a pointy end, and there is I'm going to call it an XY end. The fletching here could make the shape of an X. So when that arrow comes toward you, you see a point. And when the arrow goes away from you, you would see the X of the feathers, called fletching. So all in the middle here, the magnetic field is going away from us. It's going into the page, away from us. So we would draw a whole bunch of X's representing a magnetic field going in to the screen. On the outside of that loop, the magnetic field would be coming out of the screen, so we draw these dots like the pointy end of the arrow. X's, magnetic field going away from you. Dots, magnetic field coming toward you. And if you had a whole bunch of loops, the magnetic field around each loop of that coil is going to combine. All these magnetic fields are going to combine and make a very strong magnetic field on the inside of this, pointing into the page and kind of up and left. So here I have a coil of wire, and this is a compass, or it's a little magnet, the north end here, south end here, but that little bar magnet is gimbaled, which means it's free to move in 3 dimensions. So right now, that compass, that little bar magnet, is aligned with the magnetic field here. And as we probe around and see what the magnetic field is, we can see the magnetic field goes around that coil of wire. Same thing here, power supply. Right now, the compass is aligned with Earth's magnetic field, but as soon as I turn on the power, watch the needle, it's pointing this direction. If I switch the direction of the current, the magnetic field now goes the opposite direction. And turn the current off, there is no more movement of charges, there's no more magnetic field. Normally we would do a lab called the tangent galvanometer lab, where we can actually measure the strength of the magnetic field around a coil. And what we would do is we would have a specific amount of current running through the coil, and then we would make it wrap around in a circle once, or wrap around twice, or 3 times, or 4 times, or 5 times, and we would measure how much the compass deflects off of north. And that's how we would find the strength of the coil. And I know we've seen this before, but maybe we could even go from memory here. Go by the name of, oh shoot, I lost it. Vector, that's what it is. Applying for a new villain loan, that's what it was. It's a mathematical term, a quantity represented with an arrow with both direction and magnitude. Vector, that's me, because I'm committing crimes with both direction and magnitude. All right, we had our laughs. So, because a magnetic field has strength, magnitude, some magnetic fields are stronger than other magnetic fields, and it has direction, we can represent it with a vector. So Earth has a magnetic field, and at one location it has some strength and it has direction. So we can represent it with a vector. but we can add vectors. So if we had a compass here, that compass would align with Earth's magnetic field. And if Earth's magnetic field is pointing straight that way, the compass would point straight that way. If we introduced a second field, like a field from a coil, now we can see the magnitude of the magnetic field of the coil is much weaker, much less magnitude than that of Earth's. But if we take the magnetic field of the Earth and we add it to the magnetic field created from a coil, a loop of wire, the resultant of those is going to go like that. And the compass needle is going to align with the resultant of those two fields. And if we were to get a stronger magnetic field from the coil, the resultant of Earth's field and the coil's field would have this resultant, and the needle would align with those two. And the stronger and stronger we got it, the more that needle is going to deflect. In fact, if the needle deflected at about 45 degrees off of north, we could say the magnetic field of the coil was equal to the magnetic field of the Earth. And thinking back to SOHCAHTOA and trigonometry, the tangent of this angle equals opposite over adjacent. So the tangent of the angle of deflection is going to be the strength of the coil divided by the strength of Earth's magnetic field. Rearrange that equation and solve for coil. We could take the strength of the Earth times the tangent of the angle of deflection, and that would tell us the strength of the coil. If we define Earth's magnetic field as being one Earth magnetic field strength unit thingy, one, okay, just one magnitude of Earth. If we were to take the angle of the deflection, take the tangent of that angle, that would tell us how strong our coil is in terms of Earth's strength. So if we took the angle and then took the tangent of the angle and the answer gave us 2, that would say that the strength of the coil was twice that of Earth's. Okay, so this is the apparatus we would use. Notice how we have the wires, one wire coming in, one wire going out. That would make no magnetic field right here. But we have a coil, the current is going round and round and round and round. In order to use tangent, we had to be very certain we had a right triangle. So notice here how the needle is pointing straight that way. If current was going through this wire, and we used our right-hand rule to figure out how the magnetic field was going around that wire, we would be very careful to make sure those two were at right angles to each other. Okay, so looking at that up close, this is Earth's magnetic field like that. And if we had the coil had a magnetic field at right angles to that, like this, see how the compass needle deflected a little bit? It aligned with the resultant of those two. And that was just with one wire. If I had 2 wires, see how the compass needle deflects more? 3 wires, 4 wires, 5 wires. The more and more wires we have, the more it gets deflected. But remember, it's not the angle that tells us the strength of the field. It's the tangent of the angle. And that's just using a right triangle with trigonometry. We would find, and we won't do the lab itself, but we would find the more wraps it had, the stronger the field. In fact, with 5 wraps, the field would be 5 times as strong as if it had just 1 wrap. It's a linear relationship. Similarly, if we had 1 amp running through the coil, if we had 3 amps running through the coil, 3 times as much current, we would also get 3 times as much strength of magnetic field. So this all has the same current, but this has 2 wraps, and this would create twice the strength of field because we have twice as many charges. 3 wraps would be 3 times as strong because we have 3 times as much charge moving through there. each charge is going to have its own magnetic field. Okay. And then here, all these wires would have the same magnetic field strength because we had just one wire and lots of current, or here we have two wires but half as much current in each wire. Overall, it's just the same number of charges. Okay, now remember this. If we had a coil going around like this, current going from positive to negative, there's a magnetic field going in on the inside of that coil, a magnetic field going out. And if we just take that coil now and lay it on its side so it's in the horizontal plane, you do the same thing with your right-hand rule. The magnetic field would be going down on the inside and it would be going up on the outside. Now let's change our scale dramatically. So instead of having a loop of wire, the diameter being several inches, we now look at a single electron orbiting the nucleus of an atom. Well, that's just a charge moving around. Okay. One thing I have to clarify is that the right-hand rule applied to positive charges. If it was a negative charge, like an electron, you would use your left hand. Okay. So if I had two electrons orbiting the nucleus of the atom, but they're orbiting in opposite directions, each one's going to have a magnetic field, but the magnetic field is going to cancel because they're in opposite directions. There's no net magnetic field. If I had an atom like with 3 electrons all orbiting, well, the magnetic field from 2 of those going in opposite directions would cancel, but I would still have this net magnetic field from the 1. So that atom would have a magnetic field around it. And if I had a bunch of atoms, all with a non-paired electron orbiting, and all those orbits were in the same plane, the term is called the domain. If an atom has the electron orbiting in the same plane, we would say those two atoms have the same domain of their magnetic field. That's going to create this overall magnetic field that's going to look very similar to the magnetic field of our coil. This would be like just a coil going round and round and round and round and round. In fact, just having one electron going around has a magnetic field around it, but another atom with an electron going around and another and another and another, all those magnetic fields are going to combine and you're going to get this overall magnetic field, which looks very similar to your typical magnet. And there is a convention that we always draw magnetic field lines, and we draw them from north to south. One thing we have to be aware of is that that's on the outside of the magnet. So see how on the outside all these magnetic fields are going up, and on the inside all these magnetic fields are going down, and they just combine to make this overall magnetic field. Can you think of which end of this magnet is the north end and which is the south? Well, if we draw magnetic fields from north to south on the outside of that magnet, this would be the north end, this would be the south end. Okay. Now, normally you can't see the actual electrons orbiting, but we do typically paint one side of that magnet red, that's the north side, and blue would be the south side. And if we took an atom like a magnet like this and broke it in half, you're not going to get just a south and a north. What you've done is you've just exposed a new north, that magnetic fields are going to be coming out of here and into there, out of here and into there. You've just created 2 more magnets with a north and south, a north and south. All right, so you take that, you break it apart. You don't just get a south and a north. You get a north-south and north-south. And that's just taking what's called iron filings, and the little flecks of iron align with that magnetic field. All right, a couple more things here. If we had 2 magnets, a north and a south and a north and a south, and magnetic fields go from north to south, and they also go from north to south. You can see that when we have north on south, the magnetic fields align, and that creates an attractive force. If I had south on south or north on south, magnetic fields go from north to south and from north to south, but the magnetic field lines are bumping into each other. They're not aligning. They're pushing against each other, and that creates a repulsive force. And all magnetic fields come from moving charges. So on the center of our Earth is this metal core, and that metal core is rotating, and that is rotating relative to us. So we experience a magnetic field because of this charged inner core rotating. And it comes from convection currents, and that sustains it, and the motion of the Earth helps to keep it going. But the thing about this is that, and you're not going to like this, is that, so we see North America here, South America, and we have magnetic fields coming out of here and coming into here, which means Earth is behaving like a magnet, but this is the South Pole and this is the North Pole. The reason we call this the North Pole is because the north end of a compass points in that direction. North is attracted to south. And then one other thing is that this line here and this line here is Earth's axis of rotation. And the Earth rotates on a slightly different axis that the inner core rotates on. So the inner core creates a magnetic field that is not exactly aligned to the axis of Earth's rotation. So geographic north is right here. And then we have the magnetic north is in a little bit different location. And then the south magnetic pole is the same thing. The south magnetic pole of our Earth, our core's magnetic field, is in a place we call magnetic north. Okay. And a little bit of astronomy here. Polaris is a star that's right over our pole. And as the Earth spins in a time-lapse photography, it looks like Polaris right there pretty much stays in the same place. Now, one cool thing is, if you took a protractor, and measured how high off the horizon Polaris is, if you're standing at the North Pole, Polaris would be straight over your head. If you're standing on the equator, it would be 0 degrees off the horizon, because we'd have to look straight that way to see it. So you can measure with a protractor how high Polaris is off the horizon and determine your latitude. Okay, if you find the Big Dipper, you might recognize that. These two stars point toward the North Star. North Star is not a particularly bright star, but it just happens to be right above our poles. Okay, so this, I would say, this picture is probably taken in Florida somewhere, because that's pretty low off the horizon. Here in Colorado, if you look at it, it's right about 40 degrees off the horizon. All right, all these lines here point to geographic north, but the north magnetic north, or the south magnetic pole, is in here somewhere. And a compass is always going to point in that direction. So if you walked around this thing, the compass is always going to point that way. So these lines here go to the north geographic pole. But if you were standing here, the compass would point toward where those field lines are coming out of the Earth. The angle that it is different is called magnetic declination. And in Anchorage, Alaska, it's about 20.5 degrees. This 29 is called minutes, and there's 60 minutes in a degree. So if that was 30, that would be 30 out of 60. That's half a minute. But if you took your compass and you wanted to fly straight to Prudhoe Bay, and you followed your compass, you would be in big trouble. Okay. And it changes with time. The axis of Earth's rotation moves, and it's on its move. It's changing. So if you looked at a map here, this arrow here points to geographic north, and it tells you this compass here tells you by how far it is off. And again, that's called declination. And it's 11.5 degrees east. And that's what it was in 2008 on this map. And it's rounded to the nearest half degree. It does say that it changes by about 7 minutes. That's 7 out of 60 degrees toward the west every year. And in reality, the magnetic field of the Earth is a little complicated. At the surface, it settles into a fairly nice pattern, but more to learn about that. And that's all I have to say. I hope you learned something.